Okay, next we see continuity of composite functions. We have already seen what happens when we combine two functions algebraically, that is sum, product, which are continuous functions, then those combinations are also continuous. And next we see composition of functions. If f of x is continuous at C, where C is some point in its domain, and g of x is continuous at f of C. So that means f of C is a point in the domain of G, and also G is continuous at that point. Then the composite function or composition G circle F is continuous at C. We often make mistake in writing this. We end up writing F circle G, but keep in mind that it goes like this, no? I mean, we write the input to the right of the function on the right hand side. So because we are going to apply F first and then only we will apply G, so that's why G composition F, not F composition G. That's because the things are coming from that side. That's because we write from this side. There are other ways of writing a function also, which we will not get here, but there are. Some people write in place of f of x, some people would write xf. This may look extremely strange to us, but if we write like this, then that same composition then have to be written as f composition G, so that you do not have to change the order. There are other advantages to this notation also, but we have to keep in mind that because we are writing our inputs to the right of the function, so whenever we take the composition of f and g, you change the order. Okay, it's not, although it's f and g, it's not f circle g, but g circle f, because of this fact. But anyway, so composition of two continuous functions like this is also continuous at this point. And this can be extended to any finite number of functions. Say you have functions like this, f1, f2, f3, fn, okay, and say fn is continuous at some point C, then the previous one, fn minus 1, is continuous at fn of C, and like that if it goes and we come all the way up to f1, then the composition of all these functions would be continuous at C. And the version of this general statement where n is equal to 2 is this one. Okay, so it can be extended by a simple induction argument. Now let us see an example in which we are going to see some continuous functions where only algebraic combinations is not enough. We need to consider composition also. So that example is example 7. The following functions are all continuous on their domains, on their respective domains. So let us now see what the functions are. So the first one is of course our ordinary square root function. This function is continuous in its domain, and that fact follows from the power rule for continuity. Remember, f of x to the power m over n, that is continuous if f is continuous and for those x where this makes sense, this gives us real numbers. And in this case, those x's will form the set of non-negative real numbers, because we cannot take negative. So on the set of all non-negative real numbers, everywhere this function is continuous by theorem 6. Okay. Then another similar one is, again this one also has square root, but inside we now have a quadratic polynomial, x square minus 2x plus 5. How is this continuous? This of course has its own domain. Now we are not going to find the domain, but whatever its domain is, in that domain, first of all, the inside this radical you see this quadratic function, okay, quadratic polynomial function, that is continuous by theorem 7, because polynomials are continuous everywhere. And then you take the composition of this polynomial function and the square root function, both of which are continuous, and use this fact, continuity of composites, to claim that this function is also continuous. So that's how this one is continuous. Then C. In C you have x cos x to the power 2 over 3. The authors have made it a little complicated by having this 2 over 3 here. Okay, so let us see that the denominator is never 0. The denominator is a polynomial and it never becomes 0. For no x is this equal to 0. So there is no problem with that. The numerator is a product of two functions. One of them is this simple polynomial x. The other one, however, is cos. Okay, and we have already mentioned that cosine, sine, these two functions are continuous throughout the real line. Although we haven't proved it yet, we will prove. But right now we have to take these things for granted. So cos is continuous, x is continuous, 1 plus x to the power 4 is continuous. But what do we have over here? X to the power 2 over 3. And this is also continuous. This we already know from our previous examples and exercises. So we see that cosine of x to the power 2 over 3 is actually a composition of two functions. One of them is this x to the power 2 over 3 and the other one is cosine. Both of them are continuous, so the composition is continuous. Take the product of this continuous function and x, which is also continuous. Products of continuous functions are continuous, so the numerator is continuous. The denominator, being a polynomial, is also continuous. Moreover, it never vanishes. That's why the quotient is continuous, again by algebra of continuous functions. So that's how this is continuous. everywhere in its domain. Then we have this last one, D. X square minus 2. Okay. So here we see, let us forget about the absolute value for a moment. Let us concentrate on this quotient only, x minus 2 over x square minus 2. So it's a rational function. The numerator and the denominator are both polynomials, and there are 2 points at which the denominator vanishes, namely minus and plus square root of 2. So other than those 2 points, this rational function is continuous by theorem 7. And we already also know that the ordinary absolute value function is continuous. So what we are seeing over here is the composition of this rational function and the ordinary absolute value function. So by this result, this will also be continuous. Where actually? Everywhere except at plus or minus square root of 2. That's the thing. In fact, that is the domain of this function also. Okay, now next let us see continuous extension to a point. Here you can see that if you ignore the absolute value, you have an ordinary rational function. This rational function is continuous everywhere except at those 2 points, plus root 2 and minus root 2. Now can we change the function a little bit so that the new function becomes continuous everywhere? This next thing is about that. Continuous extension to a point. Now we won't do this only for rational functions, but in fact for any function actually. And the situation is just this. If f is a function which is not defined at C, okay, C is not a point in the domain of f. F of C has no meaning. However, at C, f does have a limit. And the limit of f of x as x approaches C exists and is equal to L. So let's just write this exists. Then we can define this function capital F. Capital F of x is defined to be equal to small f of x if x is not equal to C, and we define it to be equal to L if x is equal to C. This function is called the continuous extension of the original function to the point C. And Well, okay, of course, we should understand that here I have written it briefly. If x does not belong to C, additionally, actually what the authors have written here is that if x is a point in the domain of small f, because then only f of x has a meaning. By writing this, I actually mean to say that, okay, that x is a point in the domain and x is not equal to C. Well, C originally itself is not in the domain, but you get the point, okay. Actually what the authors have written is that if x is a point in the domain of f. Here I am just simply emphasizing the fact that x is not equal to C, and here if x is equal to C, then we define capital F to have the value L. Then clearly capital F is continuous at x equal to C. And for rational functions, if this function f is a rational function, continuous extensions to some point at which, say, the denominator is equal to 0 can be found, okay, and we are going to do that in this next example. But before we see this example, let me just go back to this. Does it even make sense what I have written here? X is not equal to C. Now actually this looks quite odd. It is not exactly conveying what I am trying to say here. Instead, let's just stick to what the authors have written. If x is a point in the domain of small f, and here if x is equal to C. Yeah, that's because C originally is not a point in the domain, as small f is not defined at C. So if our input is coming from there, then it is small f value. Otherwise, at this extra point which lies outside of this old domain, then at that point capital F has the value L. Okay. And I hope you realize why it is that f is continuous at x equal to small c. That's because if you try to calculate the limit of capital F at C, then actually you are calculating the limit of small f at C, which is L. But the value of capital F at C is also equal to L. That is why capital F is continuous at C and small f is not continuous at C. So let us now look at this rational function. F of x equal to x square plus x minus 6 over x square minus 4. And well, it's in the form of a question actually. We have to show that this rational function has a continuous extension to x equal to 2. 2 is a problematic point. We can see here that if we replace x with 2, the denominator becomes 0. So that means 2 is not a point in the domain of small f. So we need to find a continuous extension to the point x equal to 2. Like we mentioned just now, this is achieved by cancelling common factors, which is what we always do while calculating limits also of such functions. So, well, since I haven't written the exact question, I mean in the form of a question I haven't written it, so I won't write solution as well. I'll write like this. Note that I straight away calculate the limit. So this is equal to x square plus x minus 6 over x square minus 4. And this, if you see, the numerator actually is x plus 3 times x minus 2, and the denominator is x plus 2 times x minus 2, of course. Let me verify. X square, of course, we are getting 3x minus 2x is plus x, and 3 times minus 2 is minus 6. Yes. Now, because in such a limit x, the variable x is never actually equal to 2, so x minus 2 is non-zero, and so we can cancel those two factors, and we end up with this. But then by a previous result, if replacing the variable by this point does not produce any infinity or anything like that, then that will be the limit. In other words, it is just this 5/4. So now we know what the limit of this is at x equal to 2. So we can now define the continuous extension. Hence, the continuous extension of fx at, well, not at, to this point, extending to this point. We are extending the old function to this new point continuously. That's why continuous extension is minus 6 over x square minus 4. Well, you can see here if x is a point in the domain of small f. The domain of small f you can immediately figure out from here. How? See, the numerator has, it offers no problem at all. Any real number x you can put, but in the denominator you cannot put those two values, minus 2 and plus 2. So that means the domain is simply the set of real numbers from which minus 2 and plus 2 have been removed. So that's why if x belongs to, if you want you can write this set as a union of intervals, you understand, but I am writing it briefly like this. This takes less space. And five over 4 if x is equal to, oh, okay, I think there is a, hold on, is it not a bit problematic? Let me just see one thing. Okay, I have got confused. Oh no, okay, there is no confusion. All right. if x is equal to 2. I was getting confused about the point -2. Okay, -2, just like +2, originally is not a point in the domain of our original function small f, because if you put x equal to -2 also, you get 0 denominator. So -2 is not a point in the domain. However, we are finding continuous extension of f to x equal to 2. This has nothing to do with -2, and note that the continuous extension itself still is not defined at -2. It is only defined at 2. Now, if you want to extend this also continuously to x equal to -2, then you have to repeat this process with capital F. Okay, so -2 originally was also not there, now also it's not there. Fine. So that is the continuous extension. Next comes continuous functions on intervals. If a real valued function that is defined on some domain is continuous at every point of the domain, then it's called simply continuous. If we just say continuous without saying anything where or at what point, that just simply is supposed to mean that it is continuous at every point in its domain. Now, if such domains are intervals, or if such domains contain intervals, then within intervals a continuous real valued function may show some very nice behavior. So this next thing is about that. Continuity on intervals. Example 9. Now, we of course have already come across many discontinuous functions. Discontinuous functions means functions which fail to be continuous at some points in its interval. And for such functions, there are regions in the domain which usually are intervals where the function is continuous. So let's just see some examples of such functions which are not continuous everywhere but in some intervals. The first one of them is this. It is the square root, The author is not writing it as f of x, but it's the same thing. 4 minus x square. We know what its domain is. The domain is we have seen this many times already. Closed interval -2, 2. And in fact, we also know how its graph looks. It's the semicircle. Okay, it's the semicircle. On one side, it meets the point -2, 0. On the other side, it meets the point 2, 0. In other words, the radius of this semicircle is 2, and its center is at the origin, and it lies in the upper half plane. It's that thing. So this graph is continuous, this function is continuous. So this is a function which actually is continuous throughout its domain. At every point it is continuous. But the very next function is not like that. It is our familiar this function. Okay. Well, you can argue that the point 0 is not a point in the domain, but what I am trying to say is that even if you have a point in the domain of some function, it's not necessary that the function has to be continuous at that point. This is only one example in which it is not continuous at every real number. That's what I am trying to say. It is discontinuous at 0 but continuous elsewhere. You can say that it is continuous at every point in its domain. That's because 0 is not a point in its domain. That you can say, but it is not continuous at every real number. So in that respect, actually these two functions are almost the same. In their domains, they are continuous everywhere. However, this next one, unit step function, that fails to be so, and this is equal to 1 if x is non-negative and 0 if x is negative. This function is continuous on minus infinity comma 0 open interval and also on closed open 0 comma infinity. And this. So you see that unlike these two examples where every point in the domain is a point of continuity, if we want to say call such points like that. Here, however, 0 is a point in the domain of this unit step function, but actually the function is not continuous at 0. We have seen this before, right? Its graph is the x-axis on the left side of 0 and is the line which is 1 unit above the x-axis on the right side of the point 0. We know that it is not continuous at x equal to 0. It is, however, right continuous at x equal to 0, but that is a different matter altogether. So 0, in spite of being a point in the domain, is a point of discontinuity. Okay, it can happen. And let us also see this last one, y equal to cos x. Right now we just have to take it for granted that it's continuous everywhere in its domain, and the domain is, well, the domain is the entire set of real numbers. That much we already know, but continuity we are just simply mentioning it without any proof. And now finally comes a result which is very important, and you can use this result to solve, well, I should not say solve, but at least to know that some equations have solutions without actually finding the solution. So let us see. But before I state this result, let me just give you a very rough geometric idea of what we are going to talk about here. So these are your axes, coordinate axes, and say you have a function somewhere and the function has some graph. Say it's a continuous function and the graph is going in this manner, in whatever manner it can go, but it is in one piece. Okay, a single piece of curve is there, that is the graph. Now say you take any 2 points A and B, in any points in the domain of the function. Correspondingly, you will have the values of the function also. Let us see what those values are. Since the graph is arbitrary, I don't really know what we are going to get, but let's see. Okay, so corresponding to A, this is f of A, this point on the y-axis corresponds to the real number f of A. Similarly, this point on the y-axis corresponds to the real number f of B. So you have now got two numbers, two outputs, FA and FB. Let us now arbitrarily choose any real number lying between FA and FB. Say I choose this one and call it C. The question is C coming from some input? Is C the output for some input? And the answer is yes. Well, in this situation, we can see geometrically what that is. If you draw a horizontal line passing through C, then that line will intersect this curve. Exactly why since the situation is general, you just look at this figure and that point is that point of intersection. Now from there, if you drop a perpendicular on the x-axis, then you get a point here. Something, say, let me call it x naught. Clearly, C is equal to f of x naught, right? So you can see that no matter what real number you choose between FA and FB, that is actually the output of f for some input. Now, why is this happening? It is happening because of continuity and because the graph is in one piece, the graph doesn't break. Unlike this one. Let me also draw the graph of the unit step function, which is not continuous at 0. And let me show that this same situation is not true here. Let's do that. That will make everything clear. So now we draw the graph of the unit step function. Don't need much vertical space. So we know that on the left side of the origin, the graph is just the x-axis. So I make it a little thick. I don't know if it is visible from there, but this part is the graph. And this is the point 1 on the y-axis. All right. So now compare this graph with this graph. This graph is in one piece. I said one piece and I cut this here. Okay, this graph is in one piece. This is in two distinct pieces. Okay, it's broken. Now just like this A and B, let me here choose something concrete, say -1. Okay, and here say I choose 1. What is f of -1? F of -1 is, if I am calling this also f of -1 is 0. We can see that here. What is f of 1? F of 1 is 1. So this 0 and 1 play the roles of fa and fb. Now here I arbitrarily chose C. Here also let me just choose something. Okay, say C equal to 1 over 2. So now my C is here. See, just like there also these two values lie on the y-axis, here also 0 lies here and 1 lies here. So this is my C. Now is there any input for which f of that input is going to be C? No, because the function only takes two values, two distinct values, 0 and 1. That's it. It does not take any other value at all. So the discontinuity of the function, the way the function has suddenly jumped straight from 0 to 1, has allowed it to bypass all the intermediate values. Without taking on the intermediate values, it has straight away started to take 1 the moment it reached 0. However, a continuous function cannot do that. It is forced to take all intermediate values between fa and fb, maybe multiple times also, if the graph really waves like that. And this property of continuous functions, and because of this fact, is called the intermediate value property, and the theorem which states this property is called the intermediate value theorem. So that is the theorem 9. So let us now see its statement. In advanced calculus you prove these things, or in analysis also you prove these things. So the statement is, you already know the statement, I have explained it now, but still let's see. Suppose that f is a continuous function on an interval I. Okay, on an interval I. Well, if you want to know, the proof of this fact depends on something called completeness, and as the authors mentioned in the very beginning of the book, completeness is a property that is not going to be discussed in this book. It's slightly advanced for this stage. So you will see that somewhere else. And let A and B be 2 points in I, be distinct, two distinct inputs like that. If C is a real number lying between fa and fb, and the meaning of that is this: either you have this or you have this. okay, then there exists a point or number, same thing. Point, what is the name they have given? Are they calling, oh, they are not calling it. Okay, okay, the author is calling this itself, why not? Okay, not, let me not change this one, but here let me change. Although it does not matter, you can use any symbol, but let's be consistent. And the point that whose f image is going to be this one, that is C. Then there exists a point C in the closed interval a comma b. Oh, I forgot to mention that a is less than b. Nothing like that actually has been given here. For specificity, let me just assume a to be less than b, because otherwise this is empty, such that y naught is equal to f of c. And to illustrate a use of this, let us see this last example. Example 10. Here, it's a question actually. Does there exist a real number which is one less than its cube, one less than its own cube? So this question is equivalent to the equation having a solution. See, x cube minus 1 should be equal to x. Does there exist a real number x which is equal to 1 less than its cube? Which means that we are being asked to solve this equation, or rather to say whether a solution exists or not. So you consider this function, this cubic polynomial. Okay, and now cleverly the authors have calculated the values of this polynomial at 1 and 2. F of 1 will be what? This 1 and minus 1, they cancel out. We have minus 1. And what about f of 2? 8 minus 2 is 6. 6 minus 1 is 5. So we don't really know how the graph of this is going to look, but we at least know that f of 1 is negative and f of 2 is positive, and between f of 1 and f of 2 we have 0. So that 0 now plays the role of y naught here. And because we know that this function being a polynomial is continuous, so by the intermediate value theorem, there exists a c lying in the closed interval a comma b, such that f of c is equal to 0. That chosen point y naught is 0. But what does this mean? It means that c cube minus c minus 1 is equal to 0, or c is equal to c cube minus 1. So this way we have shown that there does exist at least one real number which is equal to 1 less than its own cube. Something else also, we have found such a number here in this interval. Note that it does not say what that number is, it just says there is one. And sometimes this alone can tell you many things. In fact, I think in the text the authors have given a value for C also. I did not write it. Okay, that is not that important. The main important thing is here that we can use this theorem to guarantee the existence of C. That's the thing. And with that, this section is in fact over. After this, we will again start solving the exercises. And tomorrow we have our usual, what do we have tomorrow? Group theory. Okay. So see you tomorrow with that. Until then, this is me, Lucifer from A Mathematical Room. Have a nice night.